Eight. How's it going?
Pretty good.
Good, good. Did anyone attend your class this morning?
No,
Dang.
not even my students.
Nice.
I mean, I have actually lower attendance lately, but I don't really care. I mean, they're doing fine. So,
Yeah.
and I send them emails before it's class. I think I need to stop doing that.
Yeah.
I told them the story today. They were actually laughing.
Yeah. Nice. Yeah. So do students like sign up in your class to show up in person, or do they like, or you just have like every Wednesday that you do something like that?
So the hybrid thing the thing I call hybrid is just I go in class, and I am there for whoever wants to come. And at the same time, I use my tablet and also live stream via Zoom.
I see.
And I
You
do
don't
this
like
once per
ask them
week.
if they're gonna show up, right?
What?
You don't ask them if they're like gonna show up or not.
No,
Okay.
two or three usually show up, so that's how it goes. And I usually do it Wednesday or Friday.
Right.
And this week it was Friday.
All right. Well, hello everybody. I guess first things, there as usual, there's a number theory seminar today. So today's speaker is Alvaro, as he explained yesterday. They're the same in Spanish. Lozano Robledo. So he's a professor at University of Connecticut. He does some really exciting work on torsion points and Galois representations on elliptic curves over number fields, both in the case of complex multiplication, in which case his results are competing with the results of Avi Bourdon, myself, Paul Pollock, in a friendly way, getting similar results from a different perspective. And he also does work in the non-CM case as well. And so anyway, if you're interested in Galois representations on elliptic curves over number fields, for instance, if you're taking a seminar on that topic, then you will certainly want to attend the seminar. He's an excellent speaker, by the way. So okay. Anybody have any questions about what we did? So last time we hit a high point. We really did prove what we call local class field theory. Local class field theory for p-adic fields. So the local fields of characteristic 0. And then somehow the technical reason that the proof didn't work for Laurent series fields over finite fields, we were sort of doing something with what was the point? The point was that ultimately we reduced everything to looking at the subgroup of nth powers. And it turned out that the subgroup of nth powers is easy to show that for a p-adic field, the subgroup of nth powers is cofinal among all open finite index subgroups of K star. Okay. And so, and easy to see that, if you're an nth power for all n in a p-adic field, you must be 1. So that's therefore, all we had to do was show that each of those nth power subgroups was a norm subgroup, and we did that using local symbols, using norm residue symbols. So that was just good in every way. Basically, it was it's a nice proof. It's actually pretty simple. And the fact that you're using norm residue symbols in order to do it, great. As I said before, according to some, Hilbert symbols are more important than local class field theory. At least they're more general than local class field theory. Okay. And so now we sort of, okay, but any questions about that? And this proof did not completely work in positive characteristic because in a Laurent series field, for like the 5th time, the pth powers do not have finite index inside the field. Okay. In fact, there are anyway. Yeah. All right. So so that kind of gives us our excuse to do something else. But to be honest, it's probably just an excuse. I mean, we could have done, in fact, if you follow if you read Harari, there's a chapter that we skipped. So I did chapter 9. I'm skipping chapter 10, which is local duality theorems. It's a wonderful chapter. You just can't do everything. And so he kind of takes, let's say, a more on the Galois cohomology side. So more work on the Galois cohomology side will give you the existence theorem and positive characteristic as well. So you certainly could do that. The Lubin-Tate approach, which is what I'm going to follow now, which will be valid for all local fields. So we'll certainly give you stuff on the p-adic field side as well as on the Laurent series field side. The fact that the Lubin-Tate approach kind of works verbatim in characteristic 0 versus positive characteristic is kind of like the least of its many merits. Okay, so I wanna talk about the Lubin-Tate approach now. This is really exciting for me because I've never, I think as I admitted before, I've heard about it, but I've never looked at it in detail, and I certainly haven't looked at it even in passing for like, I don't know, almost 10 years. And now I realize that it's like so close to certain things that I've been looking at in my own research, and possibly even there could be, one could still perhaps consider local analogs of some of the work on complex multiplication that I and Abby Bourdon and Paul Pollack and Jim Stankiewicz have done over the years. So I'm sort of just at the beginning of conceptualizing this. And so one thing that's possible is that it's all been done already in the local case. But anyway, so so Harari's treatment of this is fine, as usual. I eventually, late last night or sometime yesterday, I was like, well, why don't I look at the original paper of Lubin and Tate? This is an Annals paper from 1965. I will put a copy of that on ELC. I think it's like 9 pages long, so it's not, it's not super long. Harari's treatment is actually longer, than the original treatment, so he covers all the bases. I feel like he doesn't do a good job at explaining how exciting it is, though. Nor could he, because Lubin-Tate is a local class field analog of certain explicit results in global class field theory. And so following the French style, Harari can't say that because he hasn't talked about global class field theory yet. Okay, so it's kind of out of logical sequence, but at a certain point you have to say, okay, this really cool thing is out of logical sequence. Keep that in mind, and here it comes. Okay, so most of the talk that I'm going to give today is to get you excited about Lubin-Tate's approach to local class field theory, for it is, I feel, tremendously exciting. Okay, so let's motivate this. Even after class field theory has been established, right? So class field theory, what is our modern take on class field theory? Class field theory for a field K, you should give me some object which we regard as being naturally associated to K, a topological group, together with an isomorphism from the profinite completion of that topological group to the abelian Galois group of the field. So that's the modern take on class field theory. And so local class field theory is attained by this reciprocity map from the multiplicative group of K to the abelian Galois group of K, which, as we stated and just proved for p-adic fields, is an isomorphism, induces an isomorphism upon passage to the factors uniquely through the profinite completion. That's the universal property of profinite completion. And on the profinite completion induces an isomorphism. Okay, so that's definitely something, that's a lot. You can have that edifice though, but you can still ask, okay, how do I actually construct the maximal abelian extension of K? So, in all of these cases, the algebraic closure of K for either a local field or a global field certainly has countably infinite degree over K. So therefore, any algebraic extension of K is going to be like the direct limit of a sequence of finite extensions. Okay, so what does that mean? It means that there must be a literal sequence, just an infinite sequence of algebraic numbers over K that when I adjoin to K that sequence of numbers, I get Ki. Right? So that would be more explicit, right? So explicit class field theory will be, here's my field, you tell me, I guess the algebraic numbers are given by irreducible polynomials, right? Or whatever. So you give me some sequence of irreducible polynomials that if you adjoin the roots of these irreducible polynomials, then bam, you get the maximal abelian extension, right? So that would be more explicit. So let me remind you, we haven't established it yet, but there are some cases where that is known. So the first case is Q. So again, I certainly hope we will prove this theorem, but it's true that the maximal abelian extension of Q, what is that sequence of algebraic numbers? Well, the nth one is literally just your e to the 2 pi I over n, which is my favorite primitive nth root of unity in the complex numbers. Okay, and so the fact that it's easy to see, I'll recall that in fact for any field whatsoever, if you adjoin any number of roots of unity, that will give you an abelian extension. So that's just basic field theory. It's much more surprising that that's all you have to do to get the maximal abelian extension, and Q is the only number field for which the again, so another way to say this kind of comes up in some of my own work. For instance, with my former student, Marko Milosevic, and Alvaro's former student, Mike Cho. So this is what I would call Q-sic. It's the maximal cyclotomic extension of Q. So for any field, you can define K-sic, where you just throw in all the roots of unity. Okay? And so again, K-sic is always going to be contained in K-ab. The equality holds for Q. We'll see later it also holds for QP. And those are the only local and global fields for which Q-sic is equal to QApp. So why is it so easy? Anyway, so that's called the Kronecker-Weber theorem. I haven't, I'll prove it later. I'm using, again, illogically, out of logical sequence, anachronistically, I'm using this as motivation. Let me give you a slightly fancier take, which is kind of more to my taste. It's not that much fancier. So again, why do we know that the cyclotomic extension is abelian? Well, again, you can always consider the Galois action on, a field adjoin a primitive nth root of unity. Yeah, let's say the field is characteristic 0. So, we have primitive nth roots of unity in the algebraic closure for all n. And so then, yeah, if you just take any field and you look at the Galois action on K adjoin a primitive nth root of unity, then really, as part of your basic field theory, you realize that the automorphism group of K adjoin zeta of n over K is a subgroup of Z mod n Z star, because every Galois automorphism is uniquely determined by what it does to your primitive nth root of unity. And so sigma of zeta of n has to go to zeta n to some power of zeta of n, which is co-prime to m. This is by definition the mod n cyclotomic character. Okay, so I'm saying it quickly. If you've never seen this before and you want to, let me know. I could give you a much, less breathless treatment of this type of thing, but it really is just basic field theory. These are characters with values in Z mod NZ. The group Z mod NZ form an inverse system under taking quotient maps and then passing to units. And again, it's not always true that if you pass to the unit group on a surjective ring homomorphism, that you get a surjective homomorphism on the unit groups, but it's true if the rings are semi-local, for instance, and these are finite rings, so that's definitely true. Anyway, so you just take the inverse limit of these mod n cyclotomic characters, and you get the full adelic cyclotomic character, which takes its image in the inverse limit of these groups, which turns out to be the unit group of the profinite completion of Z. Here, by the way, the hat and the cross really don't commute with each other. So Z hat has an enormous, it's a ring, inverse limit of Z mod NZ. It has an enormous unit group. If you did Z hat first, you get plus minus 1. Take the profinite completion, you'd be plus minus 1. So you better profinitely complete first, then take the units. Okay. And so what's happening, again, so the splitting field of any character, here by a character on a field, in broadest terms, I mean a continuous homomorphism from the absolute Galois group of that field to any commutative group, okay? Commutative topological group. And then already, any such character is going to cut out an abelian extension just by Galois theory. So you take the kernel Galois theory is going to say that whatever the image of this homomorphism is going to be, let's say the character is taking values in a profinite group as it should. Okay, so then the image is also going to be a profinite group, and then by very, very basic group theory and by Galois theory, the image of this character is going to, there is going to be an abelian extension of L cut out by the kernel of this character, whose automorphism group is the image of the character. Okay. So literally inside K bar, you just take the you take the fixed field under the kernel of this character. Okay. The kernel is a closed subgroup. Okay, so the splitting field of that character, that's exactly the field that I just mentioned. It's sort of clear, it is K-sic. Change my notation, it's the maximal cyclotomic extension. Okay, so anyway, so this is a fancy way of realizing, so what is the abelian extension that you get by throwing in all the roots of unity? It's related to the cyclotomic character, and the automorphism group is going to be the image, isomorphic to the image of this cyclotomic character. And so what are the two facts that turn out to be the case if you do this over Q? Again, you can do this over any field of characteristic 0, but I won't be so confident as to what the image is or whether it generates the maximal abelian extension. So first of all, over Q, as I said before, it turns out that that the splitting field of this character is the entire, it's always an abelian extension. Over Q, it's the entire maximal abelian extension. And then moreover, the cyclotomic character is surjective over Q. And therefore, that tells you what the automorphism group of the maximal abelian extension of Q is. It is just Z hat cross. In other words, if you know what it does on every primitive nth root of unity, then that tells you what it is. Okay, so that's explicit. You don't get more explicit than that. If I want to generate the maximal abelian extension of Q, I throw in the nth roots of unity. I know exactly what the automorphism group of Q adjoins zeta n over Q is. It's the unit group Z mod n Z cross. Okay, so that's, I mean, if it was as simple as this for an arbitrary local or global field, we wouldn't have this course. This is unrepresentatively simple, right? The next case where you have something explicit is indeed the case of an imaginary quadratic field. So again, I'm just giving you motivation. So let me slightly simplify things by assuming that my imaginary quadratic field has class number 1. Okay, indeed, there is a more general statement for any imaginary quadratic field. Then, well, the theory of complex multiplication, one of its many applications, probably this is the classical application of complex multiplication, it generates the theory of complex multiplication will give you the maximal abelian extension of K. How does that work? I take an elliptic curve over K that has complex multiplication by the full ring of integers of K. By the way, already here I'm using the class number 1 hypothesis. In general, this elliptic curve would be defined over the Hilbert class field of K and not K itself, but okay, that's why I'm assuming it has class number 1. And so I'm going to look, now I have a mod n Galois representation on the torsion subgroup of the elliptic curve, okay? And so, geometrically, the torsion subgroup is isomorphic to Z mod n cross Z mod n. So its automorphism group is isomorphic to GL2 Z mod n Z. And so, as you'll probably learn in Alvaro's talk later this afternoon, for most elliptic curves over most number fields, you expect the image of this mod n Galois representation to be really big. In fact, if you stay away from finitely many primes, then you would expect this Galois representation to be surjective. Okay. But it has complex multiplication, so I promise you that it is not surjective. In fact, its image has to be abelian, and GL2 Z mod NZ for any n at least 2 is never abelian. And okay, you guys made me say abelian. Congratulations. Okay, right. And so what's happening in the CM case? In the CM case, the idea is that there's this extra structure here. What does it mean that the elliptic curve has complex multiplication? There's the notion of an endomorphism ring of an elliptic curve. So elliptic curves over K have this additive structure. They form an additive category if you want to be fancy about it. So I can talk about the HOM from one elliptic curve to another, and that will be a commutative group. And then I can talk about the HOM from an elliptic curve to itself, and that will be a ring. Okay, so complex multiplication says that the endomorphism ring of the elliptic curve is the ring of integers, or that's what I'm assuming, is the ring of integers in an imaginary. In general, it could be a non-maximal order. I love it, but I don't need it right now. So we'll be happy with the maximal order. And then it turns out that because the complex multiplication, because I'm working over K, it turns out that this makes the endomorphisms defined not just over the algebraic closure, but the endomorphisms are actually defined over K. It turns out, therefore, that we have an extra structure on the torsion subgroup. It's not just even the n torsion subgroup. It's not, it's isomorphic to Z mod n cross Z mod n as a Z module, but because I have this OK acting on everything, OK is endomorphisms are certainly going to preserve the n torsion subgroup. And so the n torsion subgroup is not just a Z module, it's an OK module. It's the type of OK module in which the n times any element of OK acts as 0, of course. And so therefore it's, excuse me, it is in fact an OK mod n OK module. This is some finite ring of order n squared. Okay, and it turns out that that really simplifies things. In fact, it is a free rank 1 OK mod n OK module. Okay, so as an OK mod n OK module, it's isomorphic to that. And the Galois action is not just Z linear, which is how we knew it landed in GL2 Z mod NZ. It's actually OK mod n OK linear, which means it lands in GL1 of, that was a 2 here. I think probably, yes. Okay, here we go. So because if I only use the fact that my Galois automorphisms are Z linear, then my target group is too big. I get Z linear automorphisms, but in fact, as a subgroup of GL2Z mod and Z, the automorphisms that actually respect the OK module structure is a much smaller subgroup. This is living inside. I have GL1 of this group. So yeah, like if n is a prime, for instance, this group has order roughly p to the 4th asymptotic to it as p goes to infinity, and this group has order roughly p squared. Okay, so I really am getting a much smaller image. Okay, and so the mod n Galois representation on a CM elliptic curve has image. This is called a Cartan subgroup, if you've ever heard such things. So has image in a much smaller commutative subgroup of the full GL2. And again, so therefore, since this group is commutative and this group isn't, I promise that the Galois representation construed in the usual manner cannot be surjective. But once I've cut down the image in this way, this kind of OK equivariant Galois representation might be surjective. Okay, and just as I compiled everything together by passing to the inverse limit in the case of the cyclotomic character before, I could have done that for the case of an elliptic curve. I guess I did, and I didn't read it. Over here, for any elliptic curve, you have an adelic Galois representation, which lands in GL2 of Z hat, whereas the cyclotomic character landed in GL1 of Z hat, which is Z hat cross. Now the complex multiplication is more analogous to a cyclotomic character than a non-CM elliptic curve. If you pass to the inverse limit, then the Galois representation lands inside, again, same comment as before, I take the profinite completion of OK, and then I take the unit group. Okay, and so this, whereas the original Galois, the Galois representation into GL2 of Z hat was most certainly not surjective in the CM case, this one might be. And it almost is, actually. So again, this is now getting into stuff which is not due to me at all, but is very close to the type of stuff I was doing. So it turns out that class field theory here, it is not always said in this way, but you can say it in this way. that if I just defined a map into here, if I just mod out by a tiny little group, if I mod out by the global unit group, so OK is injecting into its profinite completion, and I mod out by the group of global units, which by the way is just the group of roots of unity in an imaginary quadratic field, it's usually just plus minus 1, unless K is is Q adjoined square root minus 1 or Q adjoined square root of minus 3. Anyway, I'm modding out by a cyclic group that usually has size 2. It might have size 4. It might have size 6. Once I pass to that quotient, I've been calling this the reduced Galois representation, although not everybody likes that because it has nothing to do with reduction modulo prime. This composite homomorphism is surjective and cuts out the maximal abelian extension of K. Okay, so in fact, what I'm saying is that the automorphism group of the maximal abelian extension of K is very close. Before it really was Z hat cross on the nose. Here it's not quite that, but close enough. It's OK hat cross modulo tiny little cyclic group here. Okay, so that's explicit class field theory for an imaginary quadratic field. It uses the theory of complex multiplication. So by the way, if the order is not maximal, or if the field has class number different from 1, you can do similar things. But okay, so the upshot here is that if you allow me, let's say the field has class number 1 and is not Q adjoined square root minus 1 or Q square adjoined minus 3. Let me explain how concrete this is. So for any of the 7 other class number 1 imaginary quadratic fields, what do you do to generate the maximal abelian extension of K? You write down an elliptic curve over K, which has Cm by the full ring of integers. No problem. Silverman has a table of these elliptic curves. No problem at all. And then what do? You adjoin, I mean, there's a little thing I didn't explain here, which is related to the fact that I'm modding out by plus minus 1, and let me not explain. You can ask me about it. It turns out that really what we're saying is all you need to do is adjoin the x coordinates of the torsion points on your CM elliptic curve. That's your infinite sequence of guys. Okay. And this is so similar to what happened over Q. It's just like over Q, we have the circle and we're adjoining the torsion points. And now we have a torus, a circle across a circle, and we're adjoining the torsion points on there. So, we have n squared points of order f rather than just n as before. And we adjoin, okay, minor details, the x coordinates of those points. And that gives us the maximal abelian extension of K. So again, this is ridiculously explicit and absolutely useful. If you are trying to compute abelian extensions of K, when K is in an imaginary quadratic field, this is absolutely what you I mean, something related to this. Okay, and so if like Cox's book is a very good reference for this, primes of the form x squared plus ny squared. So part 3 of Cox's book introduces the connection between CM elliptic curves and class field theory of imaginary quadratic field. Okay. Right, and so all of this is also due to Kronecker and Weber. Okay, so this is like a late 19th century thing. And then Kronecker had I don't speak German, so a Jugendtraum, which people tell me means youthful dream. And his dream was, well, could you do something similar for all number fields, or really any other number fields? Okay, so what is Kronecker's Jugendtraum? There should be an explicit class field theory of K. What should it look like? Well, these two things kind of have this, they look similar enough so that it should sort of look similar to that. So maybe there should be, maybe you should have some very special functions. So here we have the exponential function. Here we have the x coordinate of an elliptic curve, which if you want to be a little fancier is something called the Weber function on an elliptic curve. So some, some specific rational functions on your algebraic group. Okay, and so you have an algebraic group, you have some nice rational functions on that algebraic group, you adjoin values of those rational functions on torsion points of your algebraic group. Wouldn't it be awesome if they generated the maximal abelian extension? That's Kronecker's Jugendtraum. Any questions so far? We've said a lot. No questions. All right. Everyone's like, yeah, you can try. We know. All right. So this is really hard. So by the way, Shimura, the great mathematician who died just a few years ago, my thesis was on Shimura curves. I'm an enormous fan of Shimura and his work. He has a nice, a sequence of papers. Then there's like a Springer lecture notes called Automorphic Functions and Number Theory. If you've read anything else by Shimura, you would be shocked at how short and readable his little set of lecture notes called Automorphic Functions and Number Theory is. It's like maybe the whole thing is 100 pages, and it's just so light and readable. It's amazing. So he describes, if you take a CM number field, what is a CM number field? A CM number field is a number field that is totally imaginary, has no real place, and it has an index 2 totally real subfield. Okay? So for instance, every imaginary quadratic field is a CM field, and then the next thing would be a quartic number field that has a real quadratic field inside. And so Shimura gives a partial realization of Kroneker's Jugendtraum for such number fields. So roughly, as I recall, you have to know what the abelian extension of the index 2 totally real subfield is. And then he will explain how to generate the maximal abelian extension of the CM extension over the maximal abelian extension of the index 2. And he is adjoining. He is using abelian varieties of CM type and is adjoining torsion points. Okay, so that's it's a very nice piece of work. The development of the theory of complex multiplication for abelian varieties is quite an important and beautiful thing in mathematics. I wish I understood it better myself. Is done mostly by Shimura, okay, among many other things. But it doesn't even really do the Jugendtraum for any other number field. Not in the same. I mean, this was so good. It doesn't do that. And then Henri Darmon, who was my postdoctoral advisor some years ago, he has some very exciting work which gives a partial realization of Kroneker's Jugendtraum, or maybe even something which isn't exactly that, but is nevertheless very attractive and points in that direction. He does it for real quadratic fields. Okay. And again, he has these lecture notes on elliptic curves. He has a book which I edited back in the day. Okay. Not much editing was required. Yeah. Okay, so so better luck elsewhere, actually. So this is as far as the explicit class field theory goes for number fields. But hey, there are other types of global fields, and there are also local fields. So it turns out that things are much better in the function field case. This is where Drinfeld modules came from, or at least according to some. So due to Drinfeld and then Hayes, there is a complete realization of Kroneker's Jugendtraum over any global function field. Okay, and so this uses the theory of rank 1 Drinfeld modules. And so I gave a number theory seminar talk a month or two ago, talking about so rank 1 Drinfeld modules are a function field analog of CM elliptic curves, and in particular, you use rank 1 Drinfeld modules in a way which is, in the cosmic scheme of things, excruciatingly close to the theory of CM elliptic curves, and they will build you the maximal abelian extension of your global function field. So I guess let me just to show you just a few features that are again going to get kind of analogized in the case that I really want to talk about. So so kind of in the case of Q, we had the ring of integers Z. In the case of K, an imaginary quadratic field, we had the ring of integers OK. Here we have the function field. What is RK? RK is the function field of a nice curve over a finite field. And what is our R? Our R is an affine coordinate ring that we get by taking any one closed point of the curve, or in the sense of, I mean, those who took my course last semester will at least know what I mean by closed points, since I would say that. But again, it's just a place on the function field, in this sense. Not necessarily degree 1, so just any single place. Okay, so then the ring here is the ring of all elements of the function field that are regular away from this one place, which, as we know, is a Dedekind domain with finite residue fields. Okay. Right. And so what's the point? Whatever a rank 1 Drinfeld R module is, it too comes with a system of torsion representations. The I torsion for any non-zero ideal of this ring, which is again an affine coordinate ring with finite Dedekind, finite residue fields, I can consider whatever a Drinfeld module is, I can consider the I torsion subgroup of the Drinfeld module. And as an R module, it will be rank 1 means that that the I torsion subgroup is free of rank 1 over R mod I. Therefore, its automorphism group is isomorphic to GL1 of R mod I. The I torsion R mod is just Dedekind domain stuff. R mod I is isomorphic to I inverse of R over R. Why am I saying that? Just so that you can see what happens when you take the limit. So again, just as we did in the other cases, you take the entire torsion subgroup. The entire torsion subgroup is the limit of I inverse R mod R. So that's K mod R. I didn't say this before, but that's the same as it is. You know, the roots of unity, the group of all roots of unity. What am I trying to say? The torsion subgroup of any elliptic. Sorry, let me think. What am I trying to say? Yeah, the group of all roots of unity is isomorphic to Q mod Z. Okay. And then for the CM elliptic curve case, K mod OK is the torsion subgroup of an elliptic curve. And so here we have K mod R, and then it's the R linear automorphisms of K mod R are isomorphic to R hat cross, just the same as it was in the last two cases. That's not a, you could make some, you know, whenever you have a ring of integers in a global field, all of this is gonna go through. The R linear automorphism group of K mod R is gonna be isomorphic to R hat cross. Okay. So right, and so now I get this adelic Galois representation with values in R hat cross. Again, this is because I chose it to be rank 1. In Drinfeld module land, the rank could be whatever you want. And I'm making it rank 1 in order to get an abelian Galois representation. Okay. And now, more or less, okay, so it's almost true. It's not quite true. And the way you fix it is a little bit more delicate than just modding out by this little cyclic group. This is the sort of thing that comes up in my work on. I mean, I didn't do it. I used the Drinfeld-Hayes theory of explicit complex multiplication coming from rank 1 Drinfeld modules to study the truth about torsion in the CM case. So more or less, this adelic Galois representation is surjective and cuts out the maximal abelian extension of K. It's not literally true, but you tweak it and you make it true. Okay. And so that's amazing. So that's, you know, when people have been trying to realize Kroneker's Jugendtraum, you know, in any other case aside from Q and an imaginary quadratic field for, I don't know, like about 100 years. And then Drinfeld and Hayes came along and said, no, I'll do it over a totally arbitrary global function field. Okay, so that's amazing. All right. Yeah. Okay, and so again, just to try to understand what's happening here, in each of these instances of global class field theory, we have some group scheme over our global field K, and we're adjoining torsion points. We're either adjoining torsion points, or if we want to do it, maybe we're adjoining, you know, maybe we're taking some rational function on the torsion points and adjoining the values, but it's close enough to think about it as just adjoining the field of definition of torsion points. Yeah, you see that. Okay, I've said enough. And so, yeah, so for K equals Q, the group scheme in question is just the multiplicative group of Q. The torsion subgroup here is the torsion subgroup of Q bar star, so that's roots of unity. If K is an imaginary quadratic field, the group scheme in question is the elliptic curve itself. Okay. So it's kind of funny. It's still like a one-dimensional algebraic group, but its torsion is bigger. And then for a global field, whatever a Drinfeld module is, the underlying group scheme is actually just the additive group, but then there's some extra funny R module structure that is not my business to talk about today. Okay, but you see that this is kind of the model. We have kind of a one-dimensional algebraic group. We're looking at torsion points over the algebraic group. We're getting an abelian Galois representation, and that's generating the maximal abelian extension. Okay. And so Lube and Tate do something very similar to this, not over a local field, but over a, not over a global field, but over an arbitrary local field. Okay. So we take our arbitrary local field, same as it ever is, complete discrete valued field with finite residue field. R is the valuation ring. And so what are they going to do? They're going to give us a family of, R is a much simpler ring now, it's a DVR. So the only ideals are powers of the uniformizer. Okay, and it's already profinitely complete, and so you know, R cross is the inverse limit of R mod pi to the n cross. Okay, so in this case, there is going to be a family of one-dimensional Galois representations landing in kind of this analogous thing. Okay, so it's kind of like right. So anyway, so what am I trying to say? Yeah, so the ring in question that is giving you the one-dimensional Galois representations over Q, it was Z. Over an imaginary quadratic field, it was okay. In function field land, it was an affine coordinate ring. In local field land, the ring is just going to be R, the ring of integers of the field. So that sounds nice. And so we're going to get a family of these Galois representations. Okay, I haven't told you where I'm getting this from. So again, the kernels of these one-dimensional representations, whenever you have a Galois representation with, again, as I said before, just because of the fact that this is a continuous homomorphism from the absolute Galois group into a profinite group, it's going to cut out, so the kernel of rho n is going to cut out some finite abelian extension of K, whose Galois group is a subgroup of this group. Okay. And so then the question is, well, if I take all of them together, or again, I can compile them into an inverse system if I want, and then I'll get a rho hat that goes into R star. And then the question is, am I going to get the maximal abelian extension of K with the Galois representation with coefficients in R star? You think about this and you're like, no, I'm not going to guess that, because we happen to know, we've proved in one case, we want to prove in the other case, that the maximal abelian extension of K, the automorphism group, is isomorphic to R cross Z hat, right? So R cross is giving us an abelian extension of K. It's not the full maximal abelian extension. What is it? Which piece of the maximal abelian extension of a local field is the R cross inside K cross giving us? The answer is that that's giving us the totally ramified part. Remember, the Z hat cross is the Galois group of the maximum ramified extension. Okay, let me flip back and show you. You can forget a million more technical things before you forget this. Here's our basic exact sequence, right? So profinite completion of the unit group, reciprocity map, choose the value, induced by the valuation, this Z hat gives you the Z hat, and then the kernel here, the unit group, is mapping to the abelian inertia group. So it's the Galois group of the maximal unramified extension. Okay. So right. So the answer here is that if I have an adelic Galois representation with values in R cross R cross is not the Galois group of the maximal abelian extension. It is the Galois group of the maximal unramified extension. Sorry, the Galois group of K-ab over K unram. Okay, and so that's what turns out to be the case. It turns out that the kernels of this family of one-dimensional Galois representations will generate the totally ramified part of it. So in other words, if you start with K on RAM and then take the compositum with these finite abelian extensions, you'll get the full abelian extension, and that's fine because again, I don't need anything fancy to generate the maximal unramified extension of K. Again, these are just the things that I just lift irreducible polynomials over the residue field to irreducible polynomials over my field, and they have the same Galois group. So that's the easy part. Of course, I can explicitly generate the maximal unramified extension. That's equally easy as generating the algebraic closure of a finite field, which I can do using roots of unity. Okay, using roots of unity of order prime to p. Okay. So yeah, this unramified part is cyclotomic in all cases. No problem. Okay, so that's the point. The point is that it's giving us the interesting part of the maximal abelian extension, namely the totally ramified part. Okay, so the difference here is that in all the cases that I showed you so far, there was an actual group scheme in question. We don't have a group scheme because we're not doing things locally. We're not doing things globally. We're doing things locally. So in some weird sense, a group scheme, even over a local field, is some kind of global object. And instead, we're working with the local analog of a group scheme, which is a formal scheme. Okay, but that's actually scarier than we need. I do not have to tell you what a formal scheme is. There's for instance, I think maybe in the very last section of chapter 3 of Hartshorne's book, there's a discussion of formal schemes. So roughly, if you take a group scheme and you complete it in a certain sense, then that will give you a formal group. And the way of thinking about a formal group is you take your group scheme and you take some kind of completion at the origin. So it's only looking at the group law in some types of infinitesimal neighborhoods around the origin. That's the intuition behind formal schemes, but we don't need scheme theory. We just need formal group laws. Okay, so I don't have to say formal scheme, and therefore I will not. I will stop saying formal scheme. We can phrase this in terms of formal group laws, which that's the way it works. And so formal group laws occur, for instance, in the theory of elliptic curves. So in fact, what's going to play the role, where are we going to build these representations from? We are going to build them from carefully chosen one-dimensional formal groups over R, the valuation ring. And so as I will explain coming up next, every formal group law has an endomorphism ring. And so therefore you get a notion of a formal R module is a ring homomorphism from R into the endomorphism ring of your formal group law, okay? And that sort of is playing, so this is like formal complex multiplication. I believe that's the exact term that Lubin and Tate use in their paper. So we will define a family of one-dimensional formal group laws over R depending upon this auxiliary polynomial little f that I will tell you about, not today, but in the next lecture. And again, they have this part of the Lubin-Tate setup is that if you choose f just right, then they will, and you choose a uniformizer pi, fine, then they will give you a canonical ring homomorphism from R into the endomorphism ring of their specific, this is called a Lubin-Tate formal group law. And this makes the formal group into a formal R module. And then again, I'll review this in more detail, but you remember, so a formal group is kind of like the shadow of a group when you're close to the origin. But if your ring is a complete local ring, then you can plug in points to get an honest group law. right? So if I take a complete local ring, which I certainly have, I have a complete discrete valuation ring. Basically, I can plug in points into the formal group law. I'll remind you what that is later. But the gist of it is on the maximal ideal, we get an R module structure. We get, in general, we get a group law, a commutative group law on the maximal ideal that is probably not the usual given additive group structure on the maximal ideal, unless the formal group is just the additive formal group, which it won't be. And so, yeah, so whereas if you've seen formal groups before in the study of elliptic curves, you have seen that you can plug in the maximal ideals, and then you get this, you know, you get this actual group. What role does this play? This is like the kernel of reduction when you're studying your elliptic curve over your complete discrete valuation field, right? And so in our context, we don't have an abelian variety or anything like that. We really just want the formal group law. But because this is Lubin Tate's big contribution, it's not just as a commutative group. It is in a canonical way an R module. Okay, and if it's an R module, and then, I mean, technically we're base changing to the algebraic closure, but let's worry about that later. We always were, by the way. And so, yeah, so you sort of base change to the algebraic closure. You actually plug in the maximal ideal in the separable closure, right? The integral, anyway, let's worry about that later. So you base change to the separable closure. You plug in the points of the maximal ideal. This gives you an honest to goodness R module. And then you take, which has the property that it's pi to the n torsion submodule, so literally the collection of all things that are killed by multiplication of pi to the n, has exactly the right shape. This is evidently a, you know, if I take any R module, then the pi to the n torsion part of it is certainly an R mod pi to the n module. And so it turns out, again, this is part of what they showed, that the pi to the n torsion submodule of the R module you get by plugging in the points on the formal group is free of rank 1 over R mod pi to the n. Just as before, that's the same as pi to the minus n r over r. And so if you do the entire torsion submodule, you take the direct limit here, you get k mod r. One more time, the automorphism group, the R linear automorphism group of k mod r, this is a quotient of R modules, so it's an R module. The R linear automorphism group, I don't have to profine it complete anymore because it's already complete since we're in a local field. And there's our Galois representation. Okay, and then again, adjoining the group theoretic way to say it is that the kernel of this Galois representation is going to cut out a maximal totally unramified abelian extension of K. What does that mean? That means that it's totally unramified, it's abelian, and when you take the compositum with the maximal unramified abelian extension, you'll get the entire abelian extension. Okay, so it's the complement. I remember I said that I had this short exact sequence, but the short exact sequence is split. So there is a, canonically, the R cross is the automorphism group of the abelian of K-ab over K on RAM, but because the sequence is split, you can realize that group also as the automorphism group of a totally ramified abelian extension over K, and that's what's happening here. There's some choices, though, in order for that to happen. Okay, and so, right, and then as promised, the maximal abelian extension of K, again, there's even, I just muttered some things that are more precise than what I wrote down, and we'll come back to that. But among other things, you literally do build K-ab from K on RAM, which again, as I said, is really just obtained by adjoining roots of unity of order prime to P, so Kronecker would be pleased, together with the torsion points on this Lubin-Tate formal group. Okay, so that is the Lubin-Tate approach to global class field theory. It's explicit, okay, and you go back and you can use this to prove the existence theory. Okay, so this does not obviously imply the setup of class field theory that I was talking about before, but it non-obviously implies it. Okay, so we will actually get the full statement of class field. So there is the reciprocity map occurs in this construction somewhere. I haven't shown you where it occurs yet. Okay, so that is my preview of the Lubin-Tate approach to explicit class field theory over an arbitrary local field. Most of all, it's meant to be very exciting. Do you have any questions though? So you just saw all of that and you have no follow-up questions. Really? Anyway, so yeah, maybe I should just say quickly. I mean, the next thing I'm going to do is start talking about formal groups and stuff. So the next page is like a review of formal groups. I don't think like another 5 to 10 minutes of reviewing formal groups. I might as well start that next time. So yeah, so what was I thinking? I was thinking that yeah, so I wonder. I really think there are some close analogies here. So people, if you look at the endomorphism ring of these Lubin-Tate formal groups, there's this rank that comes in terms of like similar to the rank of a Drinfeld module, and you can study let me think for a second. As far as I can see at the moment, and I need to think about it further, this could be a setup. So I have this like truth about torsion setup for CM elliptic curves, you know, which was done by Paul Pollack and I, where we analyzed the asymptotic behavior, the largest size that the torsion subgroup of an elliptic curve, CM elliptic curve over a number field can be in terms of the degree of the number field. It can be as large as a constant times d log d for infinitely many d's and no larger. And then we tried to do the same thing in Drinfeld module land for CM Drinfeld modules. And that was the talk that I gave. And so our results are complete for the rank 1 case of CM Drinfeld module. It was from Bjorn Punen's thesis. We did the rank 2 case, and we did some results in the higher rank case. And so, yeah, maybe I'll just say, so it could be the case that you could try to pursue a similar truth about torsion discussion or question. So what would you be doing? You'd fix your local field and you'd look at Lubin-Tate formal groups over a degree d extension of your local field, and you would try to understand what the largest size of the torsion subgroup of a Lubin-Tate formal group can be in terms of the degree of the extension. And this is very exciting for you guys because I barely know what I'm talking about. I literally have been thinking about Lubin-Tate formal groups for like less than 48 hours, but possibly there's a similar result. Maybe the result, it could be, it could not work out at all. There could not even be bounded or in some way. It could be like ridiculously easy because we're working with local fields instead of global fields. Maybe that makes it too easy. It could have been done in the 60s in these papers of, Lubin has some Jonathan Lubin. This was his PhD thesis under Tate. I don't know if you guys, Tate also died a few years ago. He was quite old. Jonathan Lubin is still around. He's actually active on like math.stackexchange and that sort of thing. So, anyway, but for all I know, you could pursue a Lubin-Tate version of the truth about torsion, and if it seems like there's anything, true, non-trivial, novel there, then I'll let you know. Okay. Yeah, and again, these methods are really are useful. It really is a more explicit approach to local class field theory than the standard approach, which is useful for other things. Okay. Any final questions? All right, well, I guess we have to do it. So yeah, so the next lecture is, I'm going to start off with a review of formal groups. And so sort of set everything up, set up the notion of the endomorphism ring of a formal group. And then, yeah, and then I don't know, I think I haven't fully digested all the proofs yet myself. So I don't even have a good sense of how long this will take. I think we have, at the very least, 2 more lectures on Leuventate stuff, and probably more. Okay, well, see you later. Bye.